Second type of reactions that we will focus on is the acid-base reaction. So let's start by defining acids and bases in chemistry. The first definition for acids and bases is Arrhenius definition, and it defines an acid as any substance that produces hydrogen ions in solution. So when you dissolve HCl in solution, it is gonna split into hydrogen ions and chloride ions. So that is gonna produce hydrogen ions in solution. So this is an acid. A base is any substance that produces hydroxide ions in solution. That what happens when you dissolve in AOH is gonna split into sodium ions and hydroxide ions. So that produces hydroxide in solution. So that's a base. But this definition doesn't explain why and how a molecule like ammonia is a base, because obviously when you put it in solution, you don't expect it to split hydroxide ions in solution. So that led us to the second definition of acids and bases, which is Brunsch definition. An acid is defined as any substance that will donate a proton, and a base is any substance that will accept a proton. So let's explain what does this mean. When you consider the solution of ammonia in water, water will donate one hydrogen into ammonia to produce ammonium ion and leave behind hydroxide, right? So in this case, the substance that donates a hydrogen ion is called an acid, while the substance that accepts a hydrogen ion is going to be called the base. So water in this case is going to be an acid because it donates hydrogen ion, and ammonia is a base because it accepts a hydrogen ion. If you look at the right-hand side of the equation, you can see the same possibility. The back donation of hydrogen ion from ammonium into hydroxide to make back water and ammonia. So in this case, the one that donates the hydrogen ion is an acid, which is ammonium, and the one that accepts the hydrogen ion is the base, which is hydroxide. So that's why this substance is a weak base, because both directions of the reaction are equally possible. So both of them will take place in the same time. And that description for acid base can also apply for strong acids and bases, something like HCl, where you combine HCl with water. What will happen is that HCl is going to be able to donate a hydrogen ion into water. So HCl is going to work as an acid, water is going to work as a base in this case and accepts the hydrogen, and that will form H3O plus ions and chloride ions. Okay, so that also explains the strong acid behavior. So that gives us two types of acids or bases, weak versus strong. A strong acid is any acid that is gonna completely dissociate, producing 100% of hydrogen ions in solution. So when you dissolve any sample of HCl in water, it's gonna be dissociating to 100%, producing 100% of H3O plus ions and chloride ions. That's what your solution will contain at any point of time. In comparison to that, a weak acid like acetate is going to have the two possibilities of dissociation to the ions and recombination of the ions back to the molecular acid. So that's a partial dissociation. So at any point of time, your solution of acetic acid is going to contain both the ions, the splitted ions, and the undissociated acid. It's actually going to be up to 90% undissociated acid and only like 10% dissociated ions in solution. That's why it's a weak acid, because it produces much less concentrations of the hydrogen ions in solution as compared to the strong acids. This is a list of common acids and bases classified according to their strengths. You need to know this set of strong acids: HCl, HBr, HI, HNO3, HClO4, and H2SO4, because anything else is going to be a weak acid. No matter what acid, you don't need to memorize this. Anything other than these 6 strong acids is going to be a weak acid. You also need to know these strong bases, because anything else is going to be a weak base. So that's an easy way to remember this classification of acids versus bases. How to describe an acid-base reaction when you combine a substance that you can identify as an acid with a substance that you can identify with a base. As we said, we'll apply the double exchange procedure that we learned previously. The cation of the first substance is going to combine with the anion of the second, while the anion is going to combine with the cation of the second. So you will get lithium combined with bromide plus H2O. That's a combination of hydrogen with hydroxide. And now it's time to determine the physical state. Lithium bromide is going to be a soluble substance because it's a salt of lithium, a group 1 cation that is always soluble. Water is a covalent compound that is going to be a liquid. When we look at these substances in terms of splitting, anything that is soluble, ionic compound is going to split. Anything that is solid and now liquid as well is going to remain intact. So that is going to split HBr to H plus ions plus Br minus ions. Same thing for lithium hydroxide is going to be lithium plus soluble ions with hydroxide minus soluble ions. On the second side is going to be lithium plus soluble ions plus bromide minus soluble ions. Water is the liquid. So now, as we said, anything that is solid or liquid is not going to split. So water is going to remain intact. Net ionic equation, in this case, you will cancel or cross out any spectator ion, any ion that does not undergo a change during the reaction. If you look at bromide, it remains the same before and after the reaction, so that cancels out. Lithium, it remains the same before and after the reaction, so that leaves H plus that combined with OH minus to make liquid water molecules. So that's the net ionic equation that describes an acid-base reaction between a strong acid and a strong base. If you combine weak base with a strong acid, what we will do here is we will apply Bronsted definition for the acid-base reaction, is that the hydrogen is going to migrate from the acid to the base. That will produce NH4 plus, which is going to be soluble, plus Cl minus, which is going to be soluble. If we try to look at the total ionic equation in this case, any weak acid or weak base is not going to dissociate, so it's going to remain the same. NH3 is going to remain the same. Strong acids and bases are going to split in solution. So HCl is going to split into hydrogen ions plus chloride ions. On the other side, those are soluble ions, so they're already splitted. So if you look at chloride, before and after the reaction is the same, so that's a spectator ion that is going to cancel out. So that leaves you with NH3 that is going to react with H plus ions to make NH4 plus. That's the net ionic equation that describes the acid-base reaction between a weak base and a strong acid. The other way around, if you have a combination of a strong base with a weak acid, we'll apply the same rules. Again, we'll apply the double exchange procedure. It's going to be the cation of the first substance with the anion of the second one, and vice versa, anion with the cation. So it's going to be NaF, which is going to be an aqueous solution, soluble salt, because it's a salt of sodium, a group 1 cation, plus H combined with OH is going to make water, which is going to be a covalent liquid compound. That's the molecular equation. Then we make the total ionic equation by splitting anything that would split in solution. Strong bases split into the corresponding ions. Weak acids does not. Same as weak bases, so they will remain the same. And then soluble salts are going to split to the corresponding ions. Liquid substances are not. Okay, and again, we look at this and we cancel out any spectator ion that does not undergo a change. So it's going to be sodium remains the same before and after the reaction, so that's the only spectator ion in this case. So that makes the net ionic equation the combination of OH ions with HF to make F minus ions plus water.